Well, good morning, everybody. Today I'm going to talk to you about one of the big trends that we are seeing in additive manufacturing right now, and that's the move towards multiple laser machines. Multi-laser machines help us to make parts faster and also cheaper, and that's important because it expands the range of applications in which additive can be competitive. So in the next few minutes I'm going to take you through the economics of the additive process. So we'll look at the drivers of part cost and we'll see how multiple laser machines are making a positive impact and driving those costs down. Firstly, a few words about Renishaw. We're a UK headquartered company with a broad range of interests in advanced manufacturing. We make probing systems and metrology systems for machining processes, but we're also involved in research, in healthcare, and we're a manufacturer of additive machines, specifically laser powder bed fusion machines. And I think we're quite unusual in that we are both a manufacturer of machines, but also a user. So we have a medical devices business. We make cranial maxillofacial and dental implants, for example. So we're using our own equipment every day. So there's been a big change going on at the moment between 3D printing and additive manufacturing. And what happens when we move to additive manufacturing is our focus changes. The location is moving from a research lab to the factory floor. It's not just making prototypes now or tooling, we're making products for series production, for volume production. And the focus, what's important to us changes as well. It's not just about lead time now, we're really focusing on product performance. And the value from additive really comes from delivering better performing products. We need therefore to make consistent qualified parts. It's not enough just to make a shape. Those parts have got to be consistent and certified. And so we're also seeing a move towards higher performance materials as well. So metal is growing very strongly because it delivers the high performance that's required in these innovative products. And finally, we mustn't think just about the 3D printing bit. We've also got to think about the whole process chain, because as we've seen in the previous talk, additive isn't just about the additive bit, there's subtractive to do as well in many cases. So we need to get a whole process chain that delivers a cost-effective, certified part. Okay, so let's just look at the economics of different processes. So with subtractive manufacturing, so machining, for example, we're used to there being economies of scale. So as we increase production volume, the fixed costs that we have in our process get spread over more and more parts, and so the unit cost comes down the more we make. So that's what the economics typically looks like. With additive, it's slightly different. There are some economies of scale, but they're not so great. And so the advantage that additive has tends to be where we have low volume applications where its cost is lower than conventional manufacturing. And so the additive market has been confined mostly to relatively low volume applications. But what happens if we can move that cost of additive manufacturing down? Well, then the market for AM expands and we can attack more applications and be competitive in more situations with this new technology. And so that's the big focus really behind multi-laser machines, is trying to drive that cost curve down. Another way of thinking about this is to look at the relationship between the mass of a part and its cost. And so for conventional manufacturing, so for subtractive manufacturing, we get this kind of interesting relationship where we try to achieve, when we try to achieve very low part weight, the component can get very expensive. We have to work really hard to get the last few grams of material out of our part. Or maybe we use very expensive alloys, lightweight alloys, to achieve a light weight. So the costs get really high when we get to low weight. And the opposite is true when we start to look at very simple processing techniques, then the material costs go up. So typically the minimum cost is found somewhere in the middle, where we balance the material costs and the processing costs to get a minimum cost part. And so the consequence of all of this is that when we have a product that sells into multiple sectors, typically they will choose products at different places on those cost curves. And the reason for that is they value weight and space claim differently. So for example, motorsport wants the lightest possible part. Space also want very lightweight parts, whereas industrial applications, particularly when the part is static, they don't really care about weight, they really care about cost. And so the same essential product ends up getting fragmented into a series of sub-segments to suit those different customer needs. So that's conventional manufacturing. What about additive? Additive is different. And it's different in this way. So with additive, the lower the mass of the part, the cheaper the part. So the economics are really different. And the reason for that is that we pay for the powder that we use, and it also costs us time to melt that powder and turn it into solid metal. So the lighter the weight of the component that we make, the cheaper it will be with additive. So that's a really disruptive relationship. And the secret to unlocking that is good design for AM. We need to be designing our parts using advanced design techniques to minimize the mass, and then we will get the lowest cost and will be the most competitive. And so if we can get this right, if we use advanced machines, for example, then we can flatten that cost curve down a bit and bring the cost of making our parts down, and we can bring more and more applications into a competitive situation. And so the ideal situation, I guess, is if we can drive ourselves far enough down this cost curve so we get to a point where we're actually matching the minimum cost that we could achieve conventionally, then we've got one product that could serve the whole market. Everybody would buy that product because it's lighter than everybody else, and it's also as cheap as the most expensive the cheapest conventional product. So if we can achieve that through good design for AM and through a productive AM process, then we can be really disruptive in the market that we're operating in. So that's really the goal, I guess, with AM. And so let's look at the cost drivers for a typical AM application. So we're looking here at a build you can see on the right is a set of mountain bike lugs, and these are made from titanium, so quite an expensive material. And what we see is that cost breakdown, a large part of the cost is the cost of the machine. So the machines are quite expensive. They cost you money every hour that you have them in your factory. So that time on the machine is a big factor in the total part cost. Next, we have our material costs. So the cost of that powder is quite expensive, so we need to use it wisely and recycle as much as we can. We also have post-processing costs. So the blue cost there, that's the machining and the downstream measurement and certification. And then finally, the smallest bit typically is the actual cost of labor to run the process. That's actually not generally a very big part of the total cost cycle. So what we're going to look at now is how multi-laser machines are attacking some of these things and reducing part cost. So I'm hoping my video is going to run. It is, hurrah. So this is showing you a multi-laser machine in action. So here we have 4 lasers all running at the same time. All of those lasers can address the whole of the bed. So they can be used very flexibly together to make a single part or to make a series of parts together in one build. So here you can see we're actually making a large part. I'm going to show you an image of this part in a moment. It is actually a very important part of the additive machine itself. So hopefully you can see we've got great flexibility, but also great speed here. We're going faster because we've got 4 melt pools, not just one, in the same space. And so we're moving faster. And so what we have is a single machine now with 4 lasers in it that is basically 4 times as productive as a single laser machine. So we have 4 500-watt lasers. All of those lasers can address the whole build plate, so we can use them very flexibly. And that means it's very efficient. And typically it means we're taking the capital cost element of our part down by about 50%. So the machine's a little more expensive, it has more lasers, but it's 4 times as productive. And so the ratio improves significantly. And so this is the component that we saw being made. It's the Galvo mounting block, and it's actually really at the heart of the system, and it's a key reason that we can deliver this productivity. So that the function of that part is that the steering mirrors that guide the lasers into the build chamber are mounted in that part, and they're all mounted very close together. There's conformal cooling through the part as well, so we can control the temperature, and it means we get our laser beams through a single window very close together, and it means they can all see the whole bed with a very consistent manner. So it's a really key part of the design of the machine. And so what that allows us to do, as I mentioned, is we can address the whole of the bed with all of the lasers. So it means we can run the same build with 1 laser, 2 lasers, 3 lasers, or 4 lasers. So we can decide how many lasers we want to use and deploy them appropriately. And that means that we can then assign them in whichever way we choose. And so we basically have a family of machines. They're upgradable, so the maximum number of lasers is 4, but you can buy a machine with just 1 laser and then later add lasers to it as your requirements grow. So maybe you don't have the budget or you don't have the demand yet to run a 4 laser machine. We'll start with 1 and then add lasers as your demand grows. So it gives a lot of flexibility in how we deploy this technology in production. Okay, another sort of key factor, remember the material cost element is quite a large factor in our part costs, and so it's really important that we use that material efficiently and that we get as much reuse out of the powder that we don't melt for the next build. And so the really important thing there is that we've got to preserve the quality of that powder. We must not allow it to oxidize because then we cannot continue to use it. And so on our machines, we basically keep the powder in an internal cycling system so that it never sees oxygen and moisture, so that the degradation is as low as we can get it. So that helps with powder costs. Another key factor is yield of your process. So it's no good making parts fast if they don't conform. And so one of the things we really need to consider is the consistency of the build process across the build plate. And what I'm showing you here is some examples of some tensile data that we've tested. So we've got a set of 16 samples that we've made across the bed there with our 4 lasers. And hopefully you can see all 16 of those stress strain curves are right on top of one another. So we're producing the same quality of material everywhere. And that's really important because it means you can design to tighter tolerances, you can take more weight out of your part, which means a cheaper part as well. So having that confidence in the quality is really, really important for part costs. So another thing to think about as well is confidence in our process. And so one of the things we're implementing on our latest machines is process monitoring. So what we're doing here is looking at what's happening in the melt pool and keeping a record of that so that we can analyze it. So as we melt the part, you can see a slow motion video here. It's quite a dynamic process. And so what we're doing is we're measuring that process by looking at the reflected light that comes back and sampling it at 100 kilohertz frequency. So it's very, very fast. And that allows us, you can see the optical path here, so the laser beam is going in through a focusing optic, it's being steered down to the bed, and then the returning light is what we're looking at, and we're then measuring that over time. And that gives us a record of what's happened during the process. And so what we need to do then, of course, is to analyze that data. So that data comes back, we can then start to form it into a 3D view of the component that we've just built. So here you can see some sample data, and we can look at it in various different planes and orientations, and then set thresholds on that data to look for anomalies, any areas in the part that have not processed as we would like them to process. And so we've got that record, that data, and we can compare one build to another, for example. So we have a good build, our reference build, we can compare the latest build to that and look for any small differences. So it gives us a lot more information. I'm going to keep moving. So the benefits of all of this are firstly that we get some traceability, so we can have evidence that our process has performed as we want it to. We also, of course, get a record, so we can compare that data with previous data and start to look for trends. And we can use that knowledge to improve our process and feed back into the design of the part and into the design of the process to make the process better. So it's really valuable information to have when we're developing industrial AM applications. So I mentioned that we can't just focus on the 3D printing bit of this process, and remember the post-processing cost is quite a large proportion of the total cost of our part. It can be as much as 50% in some aerospace applications. So we really need to pay attention not just to the printing bit, but also some of the downstream processes. And this is where Renishaw has some unique capabilities in that we are very experienced in controlling machining processes, for example, and making them produce accurate parts. So we're going to look at that. And metrology is at the key of this. So metrology is dimensional measurement, and that's really important because it allows us to transfer datums from one step of the process to the other and check the quality as we go so that we don't let poor quality through to later stages in our process chain. So this video is going to sort of hopefully give you an illustration of the sort of controls that we put in place in a machining application that would be finishing AM parts. And so what we're going to look at is a number of different layers of process control that we typically put in place. And so the first thing is what we call preventative controls. So those are things that we do in advance to make sure that our machine tool is in the right condition. So we've just seen a bull bar, which is checking the machine's servoing accuracy. Here we're checking the rotational accuracy of a rotary axis so that we know exactly where the part is going to move as we rotate it around. Before we start cutting, we test our tools, so we're checking the offsets of our tools and updating those automatically, so we now know our tool dimensions very accurately. And what we're doing here, you can see our additive part has just been loaded into a gauge, and that we're now finding the location of that part and creating a work coordinate system that will be sent to the machine tool. So we take our part away, load it into the machine, and now we transfer those datums into the machine tool so that we can bring the tool to the part and know that we're going to make accurate precision features. Then we get on with the machining, and we're doing the in-process control. So there we're measuring the size of a cut just before we do our finished cut to get the final size exactly right. So these are the sort of techniques that we can use to make sure not just that we make a nice shape, but that we get the functional features, the key dimensional tolerances really tight and under control. Okay, I'm going to move on because I'm running short on time. So just finally then, one of the things that we can do is support companies in their journey towards deploying additive for industrial applications. And we do that through our AM solution centers. We have one here in Shanghai, and there are a network of centers we have around the world. And what we do is that we work with companies in those centers to help them to develop their processes and build the confidence and the business case so that they're ready to make an investment in a factory for AM. So just to summarize then, we've got multi-laser systems really are the future, I think, of laser powder bed. They're vital because they allow us to go faster, and they also therefore bring the cost of parts down, and that's important. We have a family of machines that can grow with your needs from 1 laser to 4. It's the same machine, you just add lasers. So that gives you great flexibility. We're getting very consistent part quality and minimal waste of powders, and those are important cost factors, and they also drive the quality of design. And metrology, as we've seen, is really a vital link that goes through the rest of the process chain to make sure not just that the parts we build are good, but the final finished parts are good. And we have support to help you on that journey. Okay, I hope you found that useful. Please come and see us on the Renishaw stand. Come talk to me afterwards. I'll be happy to answer any questions then. Thank you very much.